Now that you've seen how you would go about training a model for medical diagnosis, let's talk about how you would go about testing such a model. You will learn about the proper use of training, validation, and test sets, and about the need for a strong ground truth in order to evaluate your models. When we apply machine learning to a dataset, we usually split it into a training and a test set. Our training set is used for the development and selection of models, and our test set for the final reporting of our results. In reality, the training data set is further split into a training set and a validation set, where the training set is used to learn a model and the validation set is used for hyperparameter tuning and giving an estimate of the model performance on the test set. Sometimes the split into a training and validation set is done multiple times in a method called cross-validation to reduce variability in our estimate of the model performance. These sets also go by different names sometimes, like validation can be called tuning or dev set, the training set can be called the development set, and the test set can go by holdout, or even more confusing, the validation set. We will stick to the terms training, validation, and test set for our purposes. We'll cover 3 challenges with building these sets in the context of medicine. The first challenge relates to how we make these test sets independent, the second relates to how we sample them, and the third relates to how we set the ground truth. Let's cover the problem of patient overlap first. Let's say a patient comes in twice for an X-ray, once in June and once in November. Both times, they're wearing a necklace when they have their X-ray taken. One of their X-rays is sampled as part of the training set, and the other as part of test. We train our deep learning model and find that it correctly predicts normal for the X-ray in the test set. The problem is that it's possible that the model actually memorized to output normal when it saw the patient with a necklace on. This is not hypothetical. Deep learning models can unintentionally memorize training data, and the model could memorize rare or unique training data aspects of the patient, such as the necklace, which could help it get the right answer when testing on the same patient. This would lead to an overly optimistic test set performance where we would think that our model is better than it actually is.